I'm giving a slide talk. I know it's very difficult to take notes from a slide talk, but if anyone wants the slides, I'd be happy to share them. Let me know. So just by way of introduction, I'd like to start kind of rough guide to different physics paradigms that I think we're familiar with. So now to each of these. Okay. So to each of these kind of classes of theories, we have some kind of category of algebraic objects associated. And in the mathematical side, of course, there are various functors going between these categories, most of which we've seen in other talks already this week. So let me say this in this talk. I'm going to be discussing a representation theory of vertex algebras. And kind of as main technical tools we're going to be using these associated Poisson algebra and Poisson variety and associative algebra, in other words, the W-algebra construction. So somehow, a sort of primordial example of this square is this, this other square. The top row is basically the PBW theorem, of course, associated to a not necessarily simple Lie algebra with universe enveloping algebra U, and its associated graded or classical limit recovers the symmetric algebra. And we also have these sort of affine versions, one of which the arc algebra J infinity of S of G appeared in Hans talk, or again that's an example of Poisson vertex algebra. With a class of vertex algebras associated as well, but now they depend also on a level parameter k, right? So if these universal affine vertex algebra Vk of G. Yeah, and let me comment too that if you have a vertex algebra in general V, then we have functorially associated objects in these other three categories. R of V with Jou's Poisson algebra, which is associative algebra as well. So explicitly the VKG, so we've also seen the definition of this already. It's the vacuum module for G hat, the untwisted affine Lie algebra associated to G. Define here in detail. And since I said we're focused on representation theory, so the representation theory of VKG, the universal, is quite easy to describe. Modules are the same thing as smooth G hat modules of level K. Things get more interesting. So somehow for a generic level, this is all you can say. The universal algebra is already simple. But at particular levels, something interesting happens. You can get some non-trivial maximal ideal and consider the simple quotient that I'll call Lk of G, which is Vk of G divided by Nk. In particular for positive integer level K, or more generally for admissible level K, so I deal with non-trivial. Yeah, and then the question is to understand the representation theory of this quotient vertex algebra. So somehow only some of the smooth G hat modules will descend to the quotient, obviously. So I'll just recall it's very standard description of what happens at positive integer level K. So let's write K in the following form as minus Joule-Coxeter number of G plus P. So now P is some integer greater than or equal to H check. And then we have this parametrization for the irreducible LKG modules given by basically the regular weights in some affine wild chamber, right? So explicitly we take the P, the weight lattice, and then it's nu that are in there, such that if you take the corresponding affine weight of level P, then its pairing with each of the simple co-roots has to be strictly positive, right? And then what are the modules? So for reasons that'll become clear later, I've introduced this row shift. So to describe the actual LKG modules, we row shift back. they're just these integrable highest weight G hat modules. So there's a picture that I spent rather too long taking up. Yeah, so here's the case of SL3, P is 4, so, and these are the regular weights inside this affine level P chamber. Okay, so rather interesting thing about vertex algebras is that under fairly general circumstances, they have interesting graded dimensions, so rather their modules have interesting graded dimensions. So if we take one of these modules, on the last slide I was calling n nu, right? We can, so they have some z plus grading, which comes from the conformal vector in the vertex algebra language. You can write down the graded dimension in this form. This turns out to converge on the upper half plane. And from the Weil-Katz's character formula, you have explicit formula for these characters. And in fact, they're modular. So that is, if you perform a modular S transformation on one of these characters, you get back some linear combination of all of the characters. This is after you introduce some normalizations. You multiply this series by some appropriate power of each of the 2 pi I tau. And you can explicitly work out the S matrix, again from the Weil-Katz's character formula. And you get this explicit formula here. So some prefactor depends on the rescaled root lattice, and a Weil group sum. Right? So a sine times some exponentials that depend on the pairing you sum over the Weil group. Okay, and it's interesting to compute these S matrices because, so there's also this theory of tensor products of modules over appropriately nice vertex algebras. So this kind of generalizes Kazhdan-Lustig theory, so this so-called Wang-Lepowski tensor product theory. And under appropriate hypotheses, so the vertex algebra in general should be rational, what's called C2 cofinite, which I'll mention later, and some other sort of minor hypotheses. The category of representations is a modular category. So this means it's a ribbon category. In a ribbon category, you get some S matrix, which you can sort of cook up by looking at the braiding and so forth. The S matrix should be non-degenerate, and that's the condition of being a modular category. In this case, you get a modular category, and furthermore, the S matrix of the modular category coincides with the S matrix that you get from the modular transformations of the characters. And so a general fact about modular categories is that you can determine the tensor product decomposition rules. So these are called fusion rules. Decompositions are irreducibles of any tensor product via this Berliner formula, some crazy sum over the S matrix. Right? So example, so SL3 at level k equals 1 has 3 irreducible modules, as we saw in the previous slide. Compute the S matrix, you get this answer. Another fact about modular tensor categories is that the square of the S matrix tells you which modules are dual to each other. So in this case, S squared is this permutation matrix. So one of the modules is self-dual, the other 2 are dual to each other. And you can compute the fusion rules, and you discover that you get the group algebra of Z3 in this case. Which again, you didn't have to compute anything because this vertex algebra is isomorphic to a lattice vertex algebra. And that's sort of well known about fusion rules are a group algebra of the discriminant form in that case. Okay, so summarizing a lot of very well-known stuff here. Slightly less well-known subject that I want to make is that, so suppose you want to actually compute these sums. You have to compute a sum over a Weil group. So for example, for SLN, that's a sum over Sn, which has n factorial elements. So as n grows, these sums become very large. But in this case of SLN, there is a trick. You can compute these kinds of sums very quickly. So you interpret, so you have 2 weights, nu and nu prime, and you want to compute this kind of sum that appeared on the previous slide. And so it's an easy observation that in an appropriate basis, you can interpret the sum precisely as the determinant of a particular matrix, right? The matrix has entries A, J, K, just given by the components, nu J and nu prime K. Okay. If you kind of stare at it for a bit, you can just see that the S matrix is given by the sort of determinant. And since it's a determinant, we could use some better method, like Gaussian elimination, to compute it. And if you go to large ranks, this really is massively faster than just doing the Weyl group sum. Okay. So I'm mentioning this now, but this is kind of going to appear towards the end of the talk again. So. Okay, so beyond positive integer levels, we have principal, co-principal, admissible levels. So these are certain rational levels of the following form. We write K as minus Wilcoxon number plus some rational number P over Q. P and Q are co-prime. Denominator should also be co-prime to the lacing number, P bigger than or equal to H check. These are called principal, admissible. There's also a set of so-called principal admissible weights of a principal admissible level, A, which I don't want to, well, so roughly speaking, these are characterized as follows. So for each weight, you can look at the associated integral co-root system. Right, so that's the set of co-roots that pair integrally with the weight. Right, so some sub-co-root system of the affine root system. And well, if you look at K lambda 0, the affine weight of level K itself, then so its integral co-root system has a set of simple co-roots given by this formula here. So since there's no finite part to the weight K lambda 0, you get all the finite co-roots. And then you also get this one extra simple co-root, right, which will be, so the usual affine co-root is minus theta check plus K, right? And what happens when you change the denominator from 1 to Q is that the first integral co-root that you get is at Q times K, right? Okay, so for a more general weight, you could ask that its set of simple co-roots is Weyl group conjugate to this kind of standard set, right? And if that happens, then you say that it's principal admissible weight. And there's a parametrization of these. So this is due to Katz and Wakimoto, who also introduced this notion of admissible weights. And again, roughly speaking, you parameterize the admissible weights of a level K by triples. The first, well, nu in this triple is just some regular dominant integral weight of level P. And then you have these other two parameters, W, an element in the finite Weyl group, and eta, some other integral weight. And these two together, eta and W, in a sense encode the affine Weyl group element that you needed in order to convert this standard simple set of simple co-roots to the set of simple co-roots of your weight. Okay, so that gives a parametrization. I say this is roughly speaking because the actual bijection is between the weights and triples of this form modulo the action of some finite group. This is like the extended affine Weyl group divided by the usual affine Weyl group. It's isomorphic to P mod Q. Okay. So, but morally speaking, it's this. They're parametrized by taking a dominant integral weight of level P, just like before, plus another pair which parametrizes how you should change the set of simple roots. And I'll just comment that there's also this notion of co-principal admissible weights, and it's sort of the same thing, except in the case where the denominator is not co-prime to the lacing number. And then everything is slightly different, but parallel. Okay, so we have the set of principal or co-principal admissible weights of level K, PRK. And another ingredient that I want to recall is now we have this admissible level K. It has a denominator Q, and there's a certain distinguished nilpotent orbit gets associated to that, we call OQ, characterized by the fact that its closure is this set, it's a set of elements that are nilpotent in order 2Q. Again, this is in the principal case. In the co-principal case, it's slightly different, similar. Okay, so returning to these sort of four paradigms. So what does I want to say? So associated to vertex algebra V, we have this Poisson algebra RV and this Jou's associative algebra Jou of V. And so first result, so I want to say is what these are in the case of LK of G, simple affine at admissible level. So it was proved by Arakawa 2015 that the associative variety, so rather this guy here is the spectrum of RV, right, which is a Poisson variety, and this is just the closure of this distinguished orbit OQ. Okay. So in particular, if K is a positive integer level, then Q is 1, and this scheme is just a point, or a fat point rather. So that's this condition, that corresponds to dimension of RV being finite. As name, they either call it Lis or C2 cofinite, right? But for more general admissible levels, of course, you get some non-trivial variety here. And in our paper, so 2022, I guess, we computed the Jou algebra as well. And it's described in this way. So we have the set of admissible ways of living K. So there's an action of the, so the dot action of the Weil group on the finite Cartan. So you quotient by that action, so we're talking about equivalence classes here. And then for each such equivalence class, take the quotient of U of G by primitive ideal, the annihilator of L of corresponding lambda. And the product of these is the Jou algebra. Okay. So the key ingredient in the proof of this is a previous result of Tomiyuki, which is that the simple affine vertex algebra admissible level is in a sense rational in the category O. So the only highest weight G hat modules, the dissenter modules of the simple quotient, are precisely the L of lambda, where lambda are the admissible weights of level K. And then using that and doing some sort of arguments with primitive ideals, you can compute the Jou algebra. Okay, and let me comment that somehow the two of the assumptions that you need for this modular tensor category story are the C2 cofiniteness, which is the finite dimensionality of this algebra, and also that the Jou algebra is semi-simple. I mean, you need a bit more as well, but those two are essential. But then you get, by this theorem of Jou, that if you have these two, then the character of the unit's modules forms some vector-valued modular form. So at least you get part of the one of the ingredients of this modular tensor category. But this is certainly not the case for admissible levels, infinite dimensional algebras. So we can sort of, well, I was going to say cure this problem. I mean, it's not necessarily a problem, but something you can do is apply Hamiltonian reduction, more precisely quantized Drinfeld-Sokolov reduction, which very briefly amounts to taking a tensor product of your affine algebra with some free fermion vertex algebra, introduce some differential, take cohomology, and this is called a W-algebra. So now this process depends on a nilpotent element. So the original story was for principal nilpotents, and then Katsura and Wakimoto introduced this generalization to arbitrary nilpotent orbit. So we get some cohomology that depends on K, obviously, and depends on the choice of this nilpotent. And then it's a theorem that this cohomology is concentrated in degree 0. So this is what I'll mean when I refer refer to a W-algebra. It's this cohomology. The interaction of this Hamiltonian reduction is with these functors is well understood as well. So at the level of the associated Poisson variety, it's known in the results of Dassault Katz and later Tomiyuki. What happens to the associated variety is just take the intersection with the Slodovy slice of F. And at the level of the Joux algebra, the kind of vertex algebra Hamiltonian reduction corresponds to the finite quantized BRST reduction, the theory of finite W-algebras. So it makes sense then to focus on a case where you take the nilpotent F to lie precisely in this orbit OQ, rather in the interior of this orbit, not on the boundary. And we'll call the result an exceptional W-algebra. So again, this terminology is not quite the same as, so I think it was Victor and Wakimoto introduced this term exceptional W-algebra. There's some other conditions. What I'm going to call exceptional W-algebra here, which means just this condition, if there's an OQ, somehow more general. I think it contains all the cases.
So your definition is exactly if F lies in
Yeah.
OQ.
Yeah. Okay. So whether we call them exceptional.
Actually, we did this. We later proved with Wimbeck and Alashvili that it's the same.
Oh, this is the same. Okay. Oh, good. Okay, so I'm calling it by the right name then. Okay, very good. So anyway, in these cases, so the intersection is precisely a point. So the Hamiltonian reduction is this, which is nice. And also, using some results, I guess, of Premet and Lusev on finite W-algebras, one can also show that the corresponding Joux algebra is semi-simple. So we know what the Joux algebra is for the affine guy. I'm going to just use some technical results about Hamiltonian reduction to show that each of the components goes to some finite dimensional semi-simple associative algebra. Okay, so that's the theorem. So from now on, if I write curly W, I mean one of these, this and Joux is semi-simple. Okay, so we want to study the representation theory of these algebras, right? They should form modular tensor categories. Maybe, I should comment, I guess. I mean, there's also this word rational, right? The vertex algebra is rational if there are finitely many irreducible modules, and there's also no extensions between the modules. So rationality implies, in particular, the Joux algebra is semi-simple. It's kind of some quasi-conjecture, long-standing conjecture that the converse is true. This has been recently claimed by Robert McRae, that if you have C2 cofiniteness and Joux algebra semi-simple and a number of other more minor conditions, then in fact these imply rationality. So we proved this theorem before that kind of sledgehammer result existed. So we prove rationality independently in some particular cases, not quite in general. But according to that theorem, rationality also follows for all of these. Okay, so some terminology of my own invention. So I'm going to call an admissible weight lambda in PRK, an admissible weight of level K. So we have its annihilating ideal and the associated variety, so it's some variety inside G. And it might happen that that's equal to this closure of OQ, and if that happens, then I'll call the weight replete. Okay. So what will generally happen is that this associated variety will either be smaller, but if it's kind of as big as possible, then I'll call it replete. So we're interested in these weights because these are precisely the weights that when you do the Hamiltonian reduction, you get something non-zero. Right? So if the variety is smaller, then when you reduce, you get 0. Okay? So this gives us a supply of modules over the affine W algebra. So we can describe these in a very nice way, for example, for sufficient sufficiently large denominator, so if Q is larger than or equal to Joule-Coxeter number, these so-called replete weights are exactly what had been called non-degenerate admissible weights, which means just that these weights are not integrable with respect to any part of the finite root system. Right? So the intersection of this set here with the finite, plus, okay, is empty. Right? So these have, so what does this correspond to in this parametrization by triples, nu, w, and eta? This corresponds to saying that eta itself, which could in general be inside this affine Weil chamber, including on the boundaries, is actually regular. So just like nu, eta is also regular. So we get a kind of pleasingly symmetrical parametrization in this case. Now it's kind of well understood that the process of Hamiltonian reduction essentially removes the W parameter here. Right? So we get a parametrization of irreducible modules for the W algebra just by the product of these two sets of regular weights of level Q, level P and level Q. I mean, not quite. Again, there's this action of this finite group involved, which kind of complicates matters, but you can kind of, well, you can deal with that.
But it's only for principle.
This is only for principle, yeah. Yeah, so, F lying in OQ, where Q is this big, means it's the principal orbit. Yeah.
Okay.
Yeah. So this quotient, I mean, you can either think of it as a quotient, or you can. There's an observation that the action of this finite group is kind of a diagonal action, and on each individual side it acts. Each weight is congruent modulo the action of this group to some element of Q, the root lattice. Right? So the weights are in the weight lattice, but they're all equivalent modulo this action to something in the root lattice. So effectively, you just turn one of these two sides into not weights, but rather roots. Now you can, in simply laced cases, you can do this either way and choose which you want to do. In non-simply laced cases, you might have a problem if either P or Q is not co-prime to the lacing number. But if one of P and Q is not co-prime to the lacing number, then the other will be co-prime. So you can always, one or other of these two equalities holds. Okay. So, and then I wrote, but I didn't say that this was this very good paper of Frankel, Katz, Wakimoto, where they worked all this out in this principal case. You find that the corresponding S matrix for the W algebra is just a Kronecker product of S matrices, so these affine S matrices, whose formula I gave on previous slide. One for level P and the other for level Q. Okay. I'll comment in a few slides more like how you do these computations. So, so the result is that what I'll call the fusion. Yeah, I should have written the name of this. So we have some corresponding modular tensor category. If you look at the Grothendieck group, then that's a commutative algebra. And this is basically just the product of two affine fusion rings, one associated to P and the other associated to Q, precisely because of this factorization of the S matrix. With this detail that on one or other of the sides you have to restrict, taking not all weights, but rather weights that lie in the root lattice. Okay. And I too should comment this is for type ADE. I guess things are more complicated in other types. Okay, so what I want to spend the rest of the talk talking about is other cases, non-principal nilpotent element F. So to do this, let me fix a good even grading for the nilpotent F. So now we have this subalgebra G0 inside G, and now I'm going to introduce it in more terminology. So let's choose the grading so that it's compatible with the our chosen root system of G. And then if an admissible weight lambda is integrable with respect to this G0 subalgebra, right? So here's integrally with these roots inside, and no other part of G, then we'll call it conservative. Okay. So why we're interested in these weights? Because so in this case, when we, it's possible to prove that this reduction here, so this W algebra, which is one of the simple, well, this is one of the components of the Joux algebra, remember, you can prove that it has a unique irreducible representation. Corresponding to that irreducible representation, there's some irreducible representation of the vertex algebra. You can also prove that that module is precisely a Hamiltonian reduction of some module coming from G hat. So what this means is that for such weights, we have a very concrete description of the corresponding W algebra module, which means in particular there's formulas for the character, which is what we want. So we'd like to be in a situation where, so you recall that we need to think about all of these so-called replete admissible weights, and we'd like that each of them, modulo the dot action of the finite Weil group, has a so-called conservative representative. This is a technical condition. If it's valid, then it means that we have this theorem. We have a rational vertex algebra, W, Hamiltonian reduction of LKG. And we have a complete characterization, in a sense, of the irreducible modules. And we have kind of some explicit way to deduce the S matrix and therefore the fusion rules for this W algebra. Let me just remark within the theorem that this includes all type A cases.
But not the other, not all the other.
Yeah, so outside type A, it includes some cases, but not all. Yeah. So in that direction, let me just remark that somehow, so this conservative condition, it's related in a way to action of the so-called component group. So we have this group G natural, a centralizer of the SL2 triple associated with the nilpotent, which in general is not connected. When it's not connected, you get an action of this group, a transitive action on this group of this group on a set of W algebra modules kind of associated with a given weight. So somehow the point is when this group is not simply connected, there's this quite delicate finite W algebra issue that you have to deal with. And we impose these conditions that I mentioned in the theorem in order for this group to be simply connected.
But for A, it is always connected.
Yeah, yeah. Sorry, I said simply connected. I meant connected. Okay. And let me just remark that so the Justine and so a paper of Justine and a very recent paper of Justine and Shigenori making inroads into this. Into some of these cases where this group is non-connected, and I think it's very interesting, but it's not what I'm going to talk about. So I'm also not going to talk about type A. So let's talk about type D and E, and at least one case where these hypotheses do hold in type D and E is for the subregular nilpotent orbit. Okay. So let me talk about these examples. So in this case, these so-called replete weights, and now, so remember in the case of principal nilpotent, the replete weights were these ones in which the intersection with the finite root system was empty. In this case, we're interested in weights where this intersection has cardinality 1. Okay. So these correspond now not to regular weights as before, but rather to weights which are not in the interior, but well, somewhere on the boundary, but kind of on one of the faces, right? So kind of the minimal amount of degenerate that you can be.
So it's inside the face.
Yeah, inside the faces, yeah. And so here's the case of SL3 again, Q is 2. So why did I change Q from 4 to 2 now? Because the only denominator Q for which the corresponding subregular W algebra is rational is when Q is 2. And then you get these 3. Somehow subregular in type A is actually not very interesting, because when you work it out, well, so here, for example, there are these 3 weights, but remember there's also an action of the of this group, which is Z3 in this case, that all these get collapsed into one irreducible module. In fact, the corresponding W algebra is somehow trivial in this case. But that's type A. Type D and E, you get some non-trivial things. So again, so we proved that you can write down the S matrix in a sense explicitly, and you again get this factorization that was first proved by Frenkel-Katz-Wakimoto in the principal case. Now this time what happens is we get something affine as before related to the numerator P, but now the denominator, we don't get something affine related to the denominator Q, we get something strange or weird. Okay. And by using explicit formulas for the characters, you can actually write down a formula for this S matrix. You get something as follows. So now the sum over the Weyl group is now turned into a sum over half the Weyl group. This is related to the fact that, so now the integral coroot system has now had one coroot go down into the finite part, and then when you apply this element W from the parametrization to that, it has to stay positive. So when you were non-degenerate, you could apply any element in the Weyl group and you could just move things freely around. Now you have this kind of one positive root which can't go negative, which kind of pins you down. So that's why essentially that's why the sum turns into sum over half of the Weyl group. I didn't say what alpha star is here. Alpha star is the unique root that has gone into G0, which for types D and E, that corresponds to the trivalent node in the Dinkin diagram. So yeah, here alpha star is just the trivalent node in the Dinkin diagram. We have a sign as before, exponential as before, and we also have this funny rational function, which involves again the Weyl group element W and a term X, which is an arbitrarily chosen element in the Cartan. Well, chosen so that it pairs non-zero with alpha star.
So it's regular. Regular.
Yeah, regular. Yeah. Oddly enough, this formula, which kind of explicitly depends on X, in fact doesn't depend on X. It's independent of X. That's true because this is computing some fusion rules, but I don't know a kind of elementary proof of this. So for any given root system, I sort of know how to prove it, but I don't really have a general elementary proof. And just some comments on where this comes from. So it really is the same strategy as in Katz and Wakimoto and Frenkel-Katz and Wakimoto. So the characters, we have to introduce some additional Cartan element, H, inserted into the characters. And then by this Weyl-Katz character formula, we have some expression, which is a Weyl group sum, basically, of theta functions, I should say here, Weyl group sum of theta functions, divided by this Weyl denominator, which is a certain infinite product, which is also a theta function. That's what we identified. Then to get when you do the Hamiltonian reduction, you basically take a limit where h goes to 0. So for the weights that we're interested in, these replete weights, in the principal case, you sort of get perfect, I mean, both of these, numerator and denominator have zeros, right? But the zeros are on the same hyperplanes, so they, in a sense, cancel out, and you can just take the limit, and it's not problematic. In the subregular case, and more generally in any non-principal case, you get this problem where we have this explicit formula, but it involves kind of a numerator with zeros on some hyperplanes and a denominator with zeros on some hyperplanes. And for the weights that we're interested in, again, the replete weights, there's cancellation between the zeros. But if you want to compute the modular transformations, do a modular transformation, you get back a sum over all characters of all modules, some of which have zeros on hyperplanes that are different than in the denominator. So you get some sort of indeterminate expression. So again, it's more delicate to take the limit, but you can still take the limit. What you do is just choose some direction. So this is where x comes from. So we just choose some x arbitrarily, take the limit along the ray as x, well, t times x as t goes to 0. And then use L'Hopital's rule. And then that's where this rational factor is from, just an application of L'Hopital's rule. Okay, so this formula, and then the next thing, interesting thing is to put on the computer and compute some examples. So, should I skip it? Yeah. So there's, all right, so I mean, in principle, it's an explicit formula, but suppose we want to work out fusion rules for some E8 type subregular W algebra. We have a sum over the Weil group, which in this case has 400 million elements. Or rather, half of the Weil group has 400 million elements. So it's just not feasible to do on a computer. So the trick that, I mean, this is the main thing I wanted to talk about today, I guess, is how can you do this kind of computation? And it goes back to this trick that I mentioned earlier in the talk about reducing to a determinant. So you have this factor involving W alpha star here. So you want to divide first into cosets in which, well, by the stabilizer of alpha star. Okay. So in this case, the stabilizer of alpha star is a copy of E7, or rather, it's the root system of E7. So then inside that E7, we find that there's an A7. So you take, the A7 inside this stabilizer. More generally, the largest type AN subroot system that you can. Then divide this big Weil group sum into sums over cosets. And then each of the sums over the type A Weil group, which is just Sn, is reduced to one of these determinants. Right? So the result is that the sum over 400 million terms is reduced to about 4,000 terms, each of which is an 8 by 8 determinant. And so this is pretty cool. So in that way, so we computed these S matrices for many cases. Let me just remark that there are some interesting isomorphisms between these subregular W algebras. Yeah, I omitted it from the notation here. So when I write W here, I mean subregular W algebra type Dn, where the denominator Q could be either, right, so for type Dn, if Q is either 2n minus 3 or 2n minus 4, then OQ is the subregular nilpotent orbit. So in both of these cases, for both of these denominators, we can do reduction by subregular and get a rational W algebra, right? It turns out both these cases are very well-known vertex algebras. They're Virasoro minimal models with parameter 2, 2n minus 3, and in this case 3n minus 2. So you can prove this because there are also explicit formulas for what's called asymptotic growth, asymptotic data of W algebras. And And if you compute the asymptotic growth for this subregular W algebra, you find the asymptotic growth is less than 1. And then using representation theory of Virasoro algebra, you can prove that it must actually be an irreducible Virasoro algebra module, so it must actually be isomorphic here. And so it was a nice test of this kind of crazy formula here that in fact when you compute the fusion rules using this S matrix, you recover the known fusion rules of Virasoro, so it's quite confident that what I'm doing here is actually correct. Then you could also look at type E6, E7, E8. E8 is my favorite case. For E8, if Q is anywhere between 24 and 29, OQ is subregular opponent orbit, so you can do reduction for any of these denominators. And you get the following result. So for denominator 34, for denominator 24, numerator 31, the W algebra is trivial. So let me comment. I mean, what does that mean for fusion rules? So, I've taken 24 as denominator because that's one of the subregular denominators for E8. Why did I take the numerator to be 31? I could take the numerator larger, and then I get some non-trivial W algebra. And what will its fusion rules be? Well, they'll be given by a product of the fusion rules of the affine vertex algebra at level P, or P shifted by Joule-Coxeter number, Kronecker product with the fusion rules of this vertex algebra, which is trivial. So from this you can deduce that the fusion rules of a general subregular E8 denominator 24 coincide with the fusion rules of some affine vertex algebra at some integer level. Okay. So similarly for other cases, so for denominator 25, then you get Virasoro 2,5, and again the fusion rules in general for this class of W algebras are given by something affine tensor product with the fusion rules of Virasoro 2,5. And I think this is one motivation for, so these levels where you let P be as small as possible, right, which is to say either equal to the Joule-Coxeter number or Joule-Coxeter number plus 1, are called boundary admissible levels. And there's sort of a lot of interest in these boundary admissible levels coming particularly from these physics people like this 4D2D duality. There's a conjecture that these are precisely the W algebras that appear from this association, right? This vertex algebra associated to some 4D theory that Tomiyuki talked about. Another reason to care about them is that somehow they're one half in this kind of product description of fusion rules, the other half of which is just some affine category. Anyway, in type E8, so these are all the three denominators where you can kind of easily identify the W algebra just by looking at asymptotic data of looking at its asymptotic data. So in Q is 27, for example, I've written a question mark here, but I mean, all this means is that the vertex algebra is what it is. Don't necessarily have a description of other terms. So as of yesterday, Shigenori and I might actually have a description of what it is. But anyway, what I can say here is that its fusion rules are the same as those of G2 at level 5, it turns out. Again, this is by explicit computation of the S matrix using the formula. Similarly, denominator 28, we get the same fusion rules as F4 at level 5. And kind of the most mysterious example is when the denominator here, 29, is as large as possible, and it's still subregular. This W algebra has 44 irreducible modules, and we can compute the fusion rules from the formula on the previous slide. But it's somehow the only case where we're not aware of any description of the fusion rules in terms of something like a quantum group, right? Or because of course these fusion rules of affine at positive integer level kind of correspond to fusion rules of quantum groups at roots of unity. And there's some kind of idea that maybe, well, anyway. We have this one case remaining where we don't really have any description of it in terms of knowing
Jethro, can't you take the numerator to be 30 in that last case?
Oh, you can.
Is that trivial?
Actually, I think it's the same if you take 30 or 31, because E8 kind of rather uniquely has only one, like E8 at level 1 is holomorphic.
That's it.
So if you go up by 1, it doesn't really change anything. Yeah, I should have written 30 actually, but it's actually the same. So just to show you that I can actually compute these things. So here I've taken one of these 34 modules and written down the matrix that corresponds to
Did you actually do this, or did you get ChatGPT to make it up?
No, I did it. I'm sure it's clear what this means, but
Did you get ChatGPT to write the code?
no, I actually, a remark on that. I wrote the code in Magma, and I lost access to Magma, and I very laboriously rewrote it all in Sage. And Sage seems to be about 1,000 times slower than Magma. So I don't know if anyone knows how to help me. Talk to me after.
Ask ChatGPT.
Oh, yeah, maybe. I mean, what I mean here, of course, is...
I know some people at Sydney, maybe they can hook you up.
That'd be good. Remember these fusion coefficients, and then I'll write n I to be n I j k. This is like 44 by 44 matrix. And I chose the most complicated module I could find and worked out this matrix for that module. This is the result. And you see some really quite crazy fusion rules. Like I think the largest integer that appears here is 92, which you can see about here. It doesn't have any simple currents, so there's not really any good description of it as like a folding or something of the affine thing. So yeah, so that's all.